quality is very, very bad. Everyone is required to stay indoors.
So aside from this COVID-19, you're still going to be required to stay indoor because of this forest fire.
Yeah. And wearing masks too, right? For both.
Yeah.
COVID and the forest fire. So.
You're still working from home?
No, I'm working from the office. We have about half of our staff is in the office.
Working in the office, yeah.
And the other half are still working from home.
Yeah.
Okay, shall we start? Welcome, everyone. I'm Tong Thot Aung, Director of AIT Solutions, Asian Institute of Technology. I'll be the host for today's talk. Let me introduce AIT Solutions and this talk. AIT Solutions is a consulting arm of AIT, and we provide and help the industry by applying AIT's knowledge, research outcomes, and expertise to the industry. Structural engineering is our key expertise of AIT Solutions, and we provide performance-based seismic design, wind tunnel testing, and structural health monitoring services to the industry. Not only structural engineering services, we have a strong IT and software development team, and we develop the structural analysis, design, and detailing software, not only structural engineering field, also other fields to meet the client needs. And we provide the customized software applications in mobile, desktop, various platforms. We initiated Meet the Expert Talk series by inviting experts from structural engineering and allied fields to share their knowledge through the online session. Let me introduce our speaker today. Mr. Ron Klemencic is a chairman and CEO of Magnusson Klemencic Associates, MKA, which is a well-known structural and civil engineering consulting firm with offices in Seattle and Chicago. He is one of the very distinguished high-rise structural engineer practicing today. He pioneered the application of performance-based seismic design in tall buildings and also co-authored Tall Building Initiative Guidelines, TBI guidelines. Most of our PBD projects were peer-reviewed by his team, and we were enlightened and broadened our knowledge in tall building design by exchanging the ideas with his team during the peer review process. To transfer this knowledge that we got from academic and practicing, we started professional master degree program in design of tall buildings in AIT last year. If any one of you interested, you can get the information from our website, and also you can contact us. Let me welcome Mr. Ron Klemencic to present Always Striving for Better. If you have any questions, please send the message in the chat box. Thank you.
Great, thank you so much, Ron. Greatly appreciate the invitation to join your group, and hope that I'm able to share some thoughts with you all that you'll find interesting and inspiring. I'm going to share my screen. Hopefully I do this correctly. Give me 1 minute here, and let's see if I go here. Can you see my screen on?
Yes, I can see your screen.
Okay, good, thank you. If at any time during my presentation, if the screen doesn't work or the audio is not working clearly, let me know, just interrupt, please. The talk today, Always Striving for Better, is not going to be terribly technical. Instead, my goal here is to offer you some, hopefully, words of inspiration and hopefully some thoughts that will cause you to think and will inspire you to go forward and challenge the world around you. And so the main ideas here are three that I'm going to share with you, three ideas that have occurred to me as a product of my experience as to how we can go about making our industry better and the world around us better. So hopefully you'll find my comments inspiring. So over the last 10 years or so, there's been a pretty substantial increase in the amount of new information and new research that has been done on a wide variety of topics, whether it be high strength reinforcing steel, on the performance of columns, on the performance of beams. Precast structures have been investigated substantially for seismic performance. Coupling beams and different ways to detail, design, and construct coupling beams have been tested, and substantial bodies of new research have been developed. Very shallow precast floor systems have been developed. Also, precast connectivity for cladding of high-rise buildings has been studied for its seismic performance. Shear walls with composite construction, whether it be embedded steel shapes in a wall panel or steel sandwich panel construction. All of these things have been researched. And beyond research, guidelines like BIM execution guidelines to better the industry's practices of BIM, the TBI guidelines that were mentioned earlier, and more recently, studies of embedded or embodied carbon in the construction industry and in buildings through life cycle assessments. All of these topics have been advanced in just the last few years. And they all came from a point of view of really being inspired by practitioners and by contractors, people out in the world facing challenges each and every day. And it resulted in advancement in our industry through partnerships with various research industries. Now, all of that was done in a very practical sort of way. There wasn't any necessarily silver bullet that inspired the thinking, and it didn't come from anybody's mobile phone. There was no app developed to come up with these ideas. These were very practical and pragmatic ideas. And so I wanted to give you some basis as to how these sorts of ideas and advancements begin, how they're advanced, and then ultimately how they're put into practice. So let me share with you of the three items I hope to convey to you, the first one. So I'll start with a little bit of a story. And the story goes like this. The sky is blue. And the grass is green. And in the United States on the freeway, the speed limit is 55. Why? And this is the first and fundamental, I'd say, idea I want to share with you, and that is the question why. When we look at the world around us, the things I mentioned, the sky, the grass, the speed limit, we take them more or less for granted. And they're just everyday things. And maybe we don't think too much about why they are the way they are. Why is the sky blue? Why is the grass green? Why is the speed limit 55? But in order to maybe make a difference in the world, understanding why is kind of the first key question to ask. And in the States, back to my analogy here. In some places, the speed limit is 60, in other places it's 65, still others it's 70. Now, once again, the question is, well, why is that? And until you really understand why something is the way it is, you're not really able to challenge it and not really be able to advance it or change it. So key number one is to try and understand why things are the way they are. So let me share another story with you in the spirit of understanding why. And I'll start again with a story. So in the beginning, God said, "Let there be light." And at some point along the way, down came from the mountaintop something that we call the building code. And the building code wasn't brought from the top of the mountain by Moses. The building code was written by people like you and by people by me who were trying to do our best, but they are not really fundamental truisms of the universe. They're meant to be the best practice. And so in the world of seismic engineering, where I work most of my practice, there's a really curious example that I'll share with you. And if you appreciate and understand why the code is the way it is, then you start to understand why it's important to question what's in the code. So in the ASCE 7 code, this is actually ASCE 710, there's a table in the code that presents the response modification factors, or R factors, for seismic design. You can see right here for a special reinforced concrete shear wall, R equals 6. And the height limit is 160 feet, or about 50 meters. And when I first discovered this provision years ago, maybe 25 or 30 years ago, when I first started practicing, it always struck me as odd. Why 160 feet? It's a very curious number. Why not 150 or why not 200? Why is it 160? It seems very precise. I did a lot of research into why it was 100 and why were shear walls limited to 160 feet. But it was really fueled by this question, well, why is it that in the first place? What I discovered was a very curious, very curious situation. It dates back to 1920 Los Angeles. And in the 1920s in Los Angeles, there was great concern by the city council about what they called the Manhattanization of Los Angeles. What they meant specifically was they were very concerned about shadows being cast on the streets of otherwise sunny Los Angeles, and they wanted to limit the height of buildings so that these shadows weren't so prevalent. And so they actually passed a law in Los Angeles in the 1920s, limiting the height of buildings to 150 feet. Now, 150, keep that in mind, that was the law to prevent shadows from being too great. A couple of decades went by and seismic engineering started to being developed in the 1940s and the 1950s. And one of the things that was discovered or was being worked on by the seismic engineers at the time was the importance of tall buildings. Let me go to this. This was the type of building that was being built at that time. Steel frame construction for taller buildings with brick infill panels or shear walls. And they viewed this type of construction as appropriate for tall buildings, but they wanted to limit this type of construction to a certain height. And they didn't quite know what height to choose. So they took as reference the 150 feet that was the law in Los Angeles from the shadow study. Well, it turns out that about the same time the structural engineers adopted the 150 feet height limit, the city of Los Angeles removed that height limit for zoning purposes. And so it became adopted by the engineering community as 150 feet limitation for these so-called dual systems, something like this. Now, it turns out when they printed the first building code that contained these provisions, the building code said buildings more than 13 stories or 160 feet. Well, that's strange, because all of the documentation up until this moment, this is the 1961 code, all of the documentation up to that point was talking about 150 feet. I dug further into this to understand, well, why did they change? And it turns out that this, in fact, was a typographical error, that it wasn't intentional, that when the code went to the printer, they made a mistake. It was intended to be 150 feet, but instead they printed 160 feet. Well, that's very strange. So the printer was mortified of their mistake and asked the code committee, what should we do? We've already printed the codes up and we've already distributed the code books. What should we do? And the committee's response was, don't worry, don't do anything. We don't really know the answer that well anyways. So from that moment in 1961 until this moment, now 60 years later, 160 feet is still in the building code as a limitation for shear wall buildings. It was a typographical error referenced from shadows being cast on the streets of Los Angeles in the 1920s. It makes absolutely no sense whatsoever. Once you understand that story and appreciate that story, it gives you some basis to ask, well, why should I even follow that then? Because it makes no sense. And the truth is, our building codes are littered with this kind of folklore in terms of code provisions. A lot of it is not based on science. A lot of it is based on committee negotiation, committee compromise. So the point of this is to always ask why things are in the building code. So today, when we're building these very ambitious buildings, like here in San Francisco, following prescriptive code language that's really has its roots from the 1920s and then on to the 1950s doesn't really make so much sense anymore. So asking why is very, very appropriate. That's why we created the TBI guidelines, is to give practicing engineers more capability to use their skills in math and in science and in physics to really do proper engineering rather than following the prescriptive language of the code, because some of the things in the code are just nonsensical. Turns out that we're pretty good as engineers at putting up hurdles. And these hurdles are things that we face, and then we feel like we need to jump over each hurdle, and then the next hurdle, and then the next hurdle, and then the next hurdle. When in fact the objective is to win the race. So why not just run in the lane that has no hurdles? This is the idea of performance-based design. Rather than following all of the hurdles of the prescriptive rules of the building code, why not go back to first principles, engineering, physics, science, and math, and run in a lane to the goal line, to the finish line, where there's no hurdles in our way. So let me offer you a couple of other things that we're thinking about right now that are also in the category of why are they this way? Of course, here's a building after the Loma Prieta earthquake in San Francisco, and substantial damage to this building. Those of you familiar with seismic engineering know that for seismic engineering, we've worked toward targeting different performance levels, from operational all the way through to collapse prevention. And we've created a framework for performance levels and as it relates to demand levels, to tune our designs to achieve certain objectives under various demand levels. And for seismic engineering, this has become the norm, the standard, and it's quite robust. And it really forms the basis of what we do today in the design, seismic design of tall buildings. But for wind design today, we're still in the dark ages. We're not working in a performance-based environment at all. We're still working in a prescriptive code environment where we define one design wind speed, and then we design our buildings to remain elastic under that wind speed. For places like Miami in this photograph where hurricanes are prevalent, or in other places like where my good friend Boise lives in Manila, where typhoons are present all the time, our buildings are very, very, very conservatively designed because they're designed to remain elastic under this peak wind demand, this peak wind velocity. Why are we doing that? Why don't we instead adopt a philosophy similar to the seismic design philosophy, where we allow different performance levels and some modest amount of nonlinear behavior in our buildings, and in doing so, make them much more efficient and much more cost-effective for our clients? Anyway, this is a question that we've asked recently. We've asked why. And we're working very diligently with many collaborators around the world to advance the idea of performance-based wind design. So you'll be seeing more about that in the coming years. But it all started with this question of why. Why are we still doing it essentially the same way that's been done for the last 70 years? Another area where we're asking the question why is in steel construction as it relates to fire protection. Here you see a standard construction type where the steel beams, the steel columns, all have a spray applied fire protection. And in addition, you see the sprinkler system. And once again, the question is, why is it that way? And the truthful answer is born mostly in folklore. There's not a lot of science behind why are we constructing and fire protecting steel buildings that way. So instead today we're advancing the idea of performance-based structural fire engineering to, again, use science and math and physics to understand temperature as just another load case for steel construction. So let me share one other thing with you here.
He's our broker. He helps look after all our money. Of course.
How much?
I don't know exactly.
What if you're not happy? Does he have to pay you back?
Nope.
Why not?
It doesn't work that way.
Why not?
Are you asking enough questions about the way your wealth is managed? Wealth management.
So another key here is not wealth management, but as mentioned by the young boy in the video, the question, why not? So once you understand why something is the way it is, the next question is, why not do it differently? And if so, you have this basis of understanding of why a code provision is the way it is, or why our practice is the way it is. Why not dream about a different way? So let me give you a few examples of where we've asked the why not question. Why not do it differently? These two buildings are both in San Francisco. The question posed here was the connection of the floor systems, the connection of the floor slabs to the shear walls in the building using a post-tension slab. That was the question. And the question was, why not locate the post-tensioning anchor, here you see here, outside of the core wall rather than inside of the core wall? By moving it outside of the core wall, it would offer great efficiencies in construction and reduce a lot of complexity. And so we asked, well, why not? And why not look at it a couple of different ways? On the left-hand side, you can see the anchors close to the wall. On the right-hand side, maybe moving the anchor a bit further away from the wall. Why can't these details not work? So we asked the question, why not? And we went into the lab, and we actually built a full-scale test module of a core wall and a slab and a column. And we reinforced it. And then we put it through the rigors of testing to prove out that this detailing approach actually had merit. The results of the testing showed that it performed quite well. And we ended up publishing the report or the test results in a journal and sharing it with the rest of the industry. And from that experience, we learned two things. One is we learned about the performance of the connection. Well, that was important. But what was more important that we learned is by sharing this information with the rest of the industry, we actually impacted many, many buildings beyond which the few we were designing. And in fact, the state of practice, at least in the US, changed almost overnight based on sharing that information. But it was all born in this question of asking, well, why not? Why not do it differently? So today in the US and in many places around the world, one of the construction types that's being investigated and built is heavy timber construction. There's a lot of interest in heavy timber construction because of its sustainability, the reduction of embodied carbon. It's become quite popular in many places around the world. So again, asking the question, why not, in this type of construction, why not grow a tree that's actually genetically engineered so that the properties of the tree better support the engineering needs of this type of construction? Because today, that's not what's done. Today, what's done is the forest industry goes out into the forest and they cut down the trees and they send them to the mill and they grade the trees, and then they take only the most select lumber to make these buildings. And there's a great amount of waste in doing that. So why not do it differently? Why not grow a proper tree to build buildings with? Why not genetically engineer a tree that has better properties, better strength, better modulus of elasticity. It's no different than many of the food crops that are already grown to feed the populations. Many of our food products have had some amount of genetic engineering done to the corn or the wheat or any other food product you can imagine. Why not trees? So again, the question here, well, why not? This is a topic that's currently being thought about and worked on. Another thing that's come up in the last few years is we've built a lot of buildings across the world where we've used a reinforced concrete core, as you see here, surrounded by steel framing, and you see the steel framing trailing well behind where the formwork is for the core. And this system has been very economical, very efficient, but as shown in this picture, what you notice is that the concrete construction is well ahead of the steel. This is because the concrete progresses at a slower rate than the steel erection. And so they must start the concrete much, much earlier, such that the steel won't catch the formwork and the casting of the concrete. That process drives the schedule for the construction of these types of buildings. So the question we asked was, why not do that differently? Why not build the core wall somehow differently? And so what we did is we went into the laboratory at Purdue University and we built some very large test specimens of some composite wall panels using steel plates on the outside, filling it with concrete on the inside with some of our professor friends, testing it in all sorts of different loading situations, researching the connectivity of those steel plate panels to the concrete inside, and ultimately came up with a new system that's now in the US called Speed Core. But it all started with this question of why not? Why not do it differently? Why must we always do it the same that we've been doing for the last 20 or 30 years? So let me move now to the third idea. So the first idea was to ask why. Why is something the way it is? With the basis of understanding of why something is the way it is, then you have the basis to challenge it and ask why not? Why not do it differently? The third idea that I'm going to share with you of the three that I want to convey is what I'll share with you next. And it talks about collaboration. So first off, imagine, if you will, that you have an idea. You have an idea that you want to share with the world and you think maybe will make things better. But oftentimes is the case for many of us, me included, we tend to run into a brick wall. We can't get our ideas to move forward. No one will listen. There's no money to be had to support our ideas. And so we get frustrated and we end up kind of returning to the way it always was. And nothing has really been advanced. What I learned through my career is that one of the keys to really moving the ball forward for our industry is collaboration. And working together, colleagues, competitors, peers, on advancing ideas. And only through working collaboratively and working together can we really get our ideas to move forward. So again, if you imagine your idea, whatever that might be, and that idea is something actually quite brilliant, if you collaborate with another group of people, whether it's in your own office, or better yet, with people from other offices or universities, but by collaborating with other people, you might find that your idea inspires even more ideas and it gets better as it goes. And not being shy about sharing our ideas and not being playing our cards too close to our chests and not sharing our ideas really stifles the advancement of the industry and actually of our practice. If you share your ideas with colleagues in the industry, what you'll learn quickly is there are funding sources that are out there amongst practitioners, amongst various foundations, the Charles Pankow Foundation, my own company's foundation, and a number of other industry groups throughout the world, throughout the US, have funds available to help people advance their ideas, whether it's the government or various private industry organizations or private companies. So if this group of really smart, energetic people works together, collaborating, asking the questions why and why not, and they do that regularly, we can really make a difference and really change the world. And then we can really make our industry improve. So as you all look into your crystal balls and think about the future of our industry, think about the future of the city in which you live, your hometown, where you're from, and how you might be able to make an impact. Keep all of these things in mind. Keep in mind asking why not, and then seek out collaborators. So when we're building the buildings of the future and the cities of tomorrow, that we actually do it really together and do it in a much better way than we've been doing it for the last 20 or 50 years. So with that, I'm certain that we can light this fuse that will allow us to really transform our industry and really propel us forward with all sorts of new ideas. If only remember these three things: asking why not, and then collaborating with one another to actually move the ideas forward. And if we do all of those things, then I'm quite certain that we can have a very bright future. We can change the world together and make it better for everyone. That concludes my formal comments. Certainly happy to take questions, have a discussion. I hope that I've offered you some inspiration and some things to think about for your future. And I very much hope I'll be able to see you all in person in the not too distant future. So I'll hand it back to you.
Thank you very much, Ron, for very informative and very motivative presentation. And thank you for sharing the importance of collaboration, importance of development, of understanding of background and reasons behind of the things that we know and apply. And also, it is important to learn, contemplate persistently, and research to improve our body of knowledge. So let's continue the Q&A session. So if you have any questions, please type in the chat box. How about our team? Any question?
You're all stunned. So while you're thinking about that, I will offer up that on two of the subjects that I mentioned in particular, the performance-based wind design and on the performance-based structural fire design. There are recently published guidelines and documents for both. And there's a couple of locations you could go to find those documents. ASCE is the publisher of both documents, but they were both sponsored financially by the Charles Pankow Foundation. So if you were to Google pankowfoundation.org, you could download those documents for free. There's no charge. And then you'll have access to that, which is the latest information that is available on both topics.
Ron, one question. One participant is asking, on the use of timber, is it really sustainable to cut down trees?
Yeah, so that's a really good question, because the truthful answer is it depends. And what it depends upon is forest management, where if a tree is cut down, but a new tree is not replanted, it's not really sustainable. But there are sustainable forestry practices where the forest is managed much like a crop of food, crop of corn, a crop of wheat is managed. And if the forest is managed thoughtfully, then it is very sustainable to regrow and plant the tree, knowing that to grow a tree worthy of building construction, it takes about 20 or 30 years to grow the tree. So this is not an annual crop like the food crops I've referenced, but it's a longer term management proposition.
Okay, so next question is, will performance-based wind design involve wind tunnel testing or just pure CFD simulation?
So the guidelines that have recently been published require wind tunnel testing. There's, at this point in time in practice, consensus that the calibration of CFT is not yet suitable to replace wind tunnel testing. It does have value, CFT, but it's more qualitative than quantitative. And so for performance-based wind design, the current guidelines, the current recommendations require not only wind tunnel testing, but also site-specific climate assessment. And so you need to have someone specialized in looking at the site itself from a historical records point of view and giving you wind demands that are appropriate for the site. Very, very similar to what's done with site-specific seismic assessment. So you need the site-specific wind demands, and then you need actual physical wind tunnel testing to determine the demands on the building itself.
Next question is, can we use the base isolation for lateral force design reduce the overall construction footprint? So base isolation can reduce the overall construction footprint?
I'm not sure I understand the question, reduce the overall construction footprint. What is you thinking about embodied carbon, or am I misunderstanding?
It is about concrete or steel usage.
Right, yeah, fair enough. So related to embodied carbon. Yes, certainly for certain building types, seismic isolation can be very effective. It's most effective for shorter, stiffer buildings. The entire I say the basic idea of seismic isolation is to shift the dynamic response of the building from what would be a very stiff building that attracts a high degree of acceleration to making the building believe it's very soft by introducing the isolation pads, and in doing so shifting the fundamental period of the building away from the peak spectral demand of the ground motion. And so for shorter buildings, 5 stories, 10 stories, 15 stories, it can be a very effective strategy in reducing seismic demands. And by reducing seismic demands, reducing the material requirements for concrete, reinforcing steel, structural steel, what have you. For taller buildings, it's not quite as effective because the benefits that you gain from shifting the period of the tall building from, say, a tall building with a fundamental period of 5 seconds, shifting it to 7 or 8 seconds, doesn't really garner you much benefit as it does in a short building where the fundamental period might be, say, 1 second or 1.5 seconds. Shifting it to 3 seconds or 3.5 seconds, it's a very big dividend. So certain building types can benefit from it greatly.
Thank you. So we, because of the limitation of the time, we will answer two more questions only. So next question is, in the use of timber, are there special considerations for fire safety?
Right, yeah, so the fire safety of timber is an ongoing research endeavor. The fundamental strategy that's commonly adopted is one that's, the specific term that is used is charring, meaning the heavy timber member, whether it's a beam or the slab of the floor, as it responds to the fire, it forms a protective layer of char on the outside of the member. And that can help the member withstand long duration fire. It's important to consider that in the design. Depending on what is your fire performance objective, you may need to oversize the beam or oversize the slab in order to have that sacrificial layer, if you will, of material. It's very similar to the same design philosophy that's oftentimes used in the sizing of steel piling that's driven into the ground and when one is considering corrosion. That if you oversize the pile by a certain amount, you can ensure the long-term performance in a corrosive environment just by oversizing it. Well, it's similar for heavy timber construction with regards to fire. The part of heavy timber construction that needs a lot more attention and a lot more research and work is in the area of connectivity, connecting beams to columns, connecting floor slabs to beams, connecting beams to walls. The connection performance is not really well understood under fire demands. And so a lot more research needs to be done in that area to ensure that we're designing buildings properly.
Okay, so the last question is, when new TBI guideline will be released as LATBS TC 2020, which is released just last few months?
Right. Yeah, so I can report to you that at the moment, there's no work ongoing to release a new TBI version. The most recent version is TBI version 2.03, which I believe was published in 2017. So if you're not using 2.03, once again, you can get that through a variety of websites downloading for free. The Panko Foundation is another funder of that, so you can get it from the Panko Foundation, but there's no current ongoing effort to update that in the next year or two, so it will remain as is for probably the next several years. The LA document tends to be updated every few years, and you're right, they just published 2020 a new version. I'm not sure when their next version will be, but my guess is it will be at least 2 to 3 years from now. With both documents, I'd say performance-based seismic design has matured a great deal over the last 20 years. And so as new versions are published, the changes and the updates are becoming less substantial. It's more minor adjustments and not large changes. So I'd say that performance-based seismic design at this point is pretty stable. It's always good to have the latest document, of course, but there's, like I say, nothing new coming from Peer TBI in the near term. And LA just published theirs this last year. So.
Thank you, everyone. So let's conclude our session, and I look forward to seeing you in coming events, coming talks. Have a good day. Stay safe. Thank you very much, Ron. Good night.
Yeah, thank you so much. I really appreciate it. Thank you for inviting me, and I hope everyone stays healthy and safe. And I hope to see you maybe next year in Bangkok.
Thank you.
Okay, bye-bye.
Bye.